Hello, welcome to the final presentation for the show and tell. So I'm Teck and this is Fabian. So today we're actually trying to present some of the algorithms. What we have here today is Tower HANOI. It's actually one of the most classical approach to recursive algorithm. So this is actually, back in the days, it was actually invented by Sir Lucas. He's one of the famed French mathematician in 1883. So Tower HANOI actually originated back in the days where there was an ancient temple called Hanoi. So yeah, total with 3 towers and 64 golden discs. So you can see some of the discs that are stacking on top of this like little towers. You can call it pecks also. So at the point of time, the priests, right, there were few priests in the temple. So it was once said that in order to move 64 discs, golden discs, from one tower to another, you actually have to go through each of the pack to move it recursively. And in order to complete this 64 golden discs from one tower to another, the world will end before they even try to finish it. So this is an explanation how it goes. So for every single additional golden disc that is stacked on top of it, you will actually see that there's some of the steps involved. But there's a lot more of the golden discs being added on top of this packs. You will realize that the amount of steps it takes to move those discs recursively is going to take a lot more. So the rules are actually the larger disc, right? They cannot be stacked on a smaller disc. So what you're trying to see here is that it adds a lot of restriction to the packs itself. So you can see that the algorithm itself is actually very close to a binary tree. So when you actually split them up, you realize like for every single steps that you have inside there, you will actually you have to take a lot more steps. So within this binary tree, let's say if I have like move for 4, so I will add in another groups of these steps into another binary tree. So it appears like there will be a lot more steps for each of the golden discs added. So it turns out that the priests who are trying to get all the 64 golden discs from one tower to another, it's impossible to finish it. So you can see the complexity within this, the amount of moves. So for every single additional golden disc, it will take a lot more steps. So complexity can be actually summarized to O to the power n. So we are not just ending here, because a lot of time in this CT class we are talking about time complexity. So today we want to introduce another thing which is called space complexity. So I will pass on the time to Fabian to talk about space complexity.
Where should I click this? Hello. Okay. So you can see over here, the algorithm that I'll be presenting today is actually dynamic programming. So please don't misunderstand this statement, because I realize it's very misleading. Brute force and greedy is still needed, even if you have dynamic programming. So this is just a very simple concept that basically it just stores the results of your sub-problem to avoid repetitive computation. In another word, it reduces your complexity. A better illustration will be something like that. We all know that time is money, right? So we'll be reducing the time complexity from 2 to the power of n to n. So now to you might be like, what does that mean? Don't know, right? Yeah. And also for the space complexity is wrong. It's actually O(n) to O(n), so there's no change. So for you to use dynamic programming, you need to fulfill 2 main properties. First is optimal substructure, when your optimal solution of a problem can be obtained from optimal answer of its subproblem and overlapping subproblem, where the solution of subproblem is required more than one time. Very cheap. Never mind. Let me explain in the next slide. So any combination of this number can give us a sum of 12. How are we supposed to find the solution for this? So one common subset that we can use is 1 plus 3 plus 8, right? And yes, we know that if 1 plus 3 plus 8 can give us the answer of 12, we don't really need to go one extra step to check if 1, 3, 8, and 6 can fulfill this particular problem, because it already says that this works, so this automatically will just work. Meanwhile, for overlapping subproblem will be something like your Fibonacci. So recursive, right? Your 7 will call for 6 and 5, then it will just keep on recursively get all the solutions and of the subproblems. But with dynamic programming, this is all we need to find. We just need to find one round, which basically from 2 to the power of n, and we reduce it to on by storing it in an array, which works like this. Okay, this is the tabulation approach. It's very, very rare for people to use it, but it's just like normal storing of value, which I'm not going to talk about it today. But the main thing that we want to share is the memoization approach. So this is a normal recursive for Fibonacci. For Fibonacci. And in short, every time when we run the recursion, we'll store the answer in an array or dictionary, whichever they prefer. And for this, we will skip a lot of steps because we don't need to go through every single recursion. So this is the main difference between the both method, but mainly is for tabulation, you go from a bottom-up approach, and for memoization, you go from a top-down approach. Yes. So now we have a little lab test, but don't worry, it's only for the presenters. Okay.
Everybody still remember the lab test that you have regarding question 3 where you have the coin flipping? Okay, we start with Fibonacci, sorry.
Okay, so you can see from here, like Fibonacci itself, right? This will be a normal recursive for Fibonacci. So I'll run this function, and then I'll compute the time needed for just Fibonacci 35. It will take a little while to calculate, which will give you the time as 5.54. But with this memoization method, this is how much it will take. Basically, you reduce the time complexity by a lot. And the good thing is, you can like just increase it to 1000 and it will still take a lot lesser compared to the original recursion. So in case, right, your finals, they're going to ask you like, oh, please give me a reduction step for this recursion. You can just use this method. Yeah, I'm not really sure what is the question, but yeah. And pretty sure this looks familiar to all of you guys, right? The stairs climbing problem or something along the line. So it works the same way. When I run this, and I run for number of way to be 30, it's going to take quite some time for it to compute it, because like it will just go down the tree and stuff like that. Yeah, so total it takes 10 seconds. But if I'm going to store this in an array for every time it's recurs, this is how fast it will run. And basically, the main point of this concept is to trade off some space to gain a lot more efficient method for time efficiency. And don't forget, greedy algorithm is still important. Yes. not because it's coming out for finals, but because there are certain kind of questions that it can't be solved using dynamic programming. And I'm going to run my last code, which is this. Okay. Is it
Any questions for Fabian and Teck?
So it's not constant space, right? When
Sorry?
it's not ON space at the start, right? Isn't it O1 to ON, not ON to ON?
Oh, so it's a typo. It's actually ON to ON. Because initially I thought recursion is a O1 space complexity, but apparently whenever you call a method, it's being recorded in the system itself. So it isn't really a trade-off. Hmm?
Yeah, so this is basically the main point of what we are trying to do with the space complexity. We are just only storing for the left side of it, and we just remove the rest.
Alright, thank you.
Thank you.